Long before telescopes or writing, people measured the universe with stones and shadows. This video reveals how the first astronomers achieved a scientific precision we can barely believe, using only these simple tools. You will discover that ancient monuments around the world are not just ruins, but sophisticated celestial observatories. How did a single stone's shadow predict the changing seasons? And what profound secrets are encoded in the silent alignments of forgotten temples? This story uncovers a forgotten genius that connects us all to the cosmos. What do you think it means to truly see the sky? The night sky was a primal clock for our earliest ancestors. They saw the sun's journey shift with the seasons, watched the moon reliably swell and shrink, and recognized the stars as a rotating map. This was not mere stargazing, it was a fundamental need for survival. Knowing when the rains would come, when the herds would migrate, when to plant and when to harvest, all of this was written in the heavens. Their first observatories required no construction, only observation. A hunter might notice that the sun rose directly over a distant peak only on the longest day of the year. Another might see the winter solstice moon framed perfectly by a split in the rocks. These natural alignments were the original calendar, a celestial agreement with the earth itself. This profound realization that the universe followed a predictable rhythm was humanity's first great scientific breakthrough. But how do you move from noticing a pattern to building a permanent record of it? The answer began with a single stone, deliberately placed to catch a shadow. This new kind of detective, the Archaeoastronomer, pieces together a lost science with a surprisingly simple toolkit. They arrive at an ancient site not with powerful telescopes, but with compasses, theodolites, and a deep familiarity with the sky's slow, predictable dance. Their investigation begins with the stones themselves, measuring the precise orientation of a tomb's entrance or the alignment of massive pillars. They study carvings on rock faces, asking if a spiral might chart a star's long cycle or if a burst of Pex could record the sudden, brilliant appearance of a supernova. A central concept they rely on is the horizon calendar. Imagine standing in one spot day after day and watching the point on the horizon where the sun rises. Throughout the year, that point marches steadily back and forth. The solstices are the turning points, the farthest north and south the sun will ever reach, while the equinoxes mark the center, when day and night are of equal length. By finding a stone that perfectly frames the solstice sunrise, or a corridor that floods with light only on the equinox, the Archaeoastronomer confirms a deliberate design. This fusion of dirt archaeology and celestial mechanics transforms silent ruins into functional observatories. To understand the sheer brilliance of this ancient engineering, we can look to a windswept Scottish island where a stone circle reveals its secrets through the longest shadow of the year. On the windswept Salisbury Plain, the great stones of Stonehenge have guarded their secret for millennia. We once thought it was just a temple, but we now know it was something far more precise, a monumental computer built of earth and stone. Its primary function was to mark the solstices, the pivotal turning points of the year. The massive heel stone, standing alone outside the main circle, acts as a perfect celestial foresight. On the summer solstice, the sun rises directly over its weathered peak, sending a blade of light that slices through the monument's center. This was not a vague symbolic gesture, it was a precise, predictable, and repeatable astronomical event. But the builder's ambition reached even further, capturing the more complex dance of the moon. The careful arrangement of the towering sarsen stones creates a series of sightlines that track the moon's most extreme rising and setting points across its long, 18.6-year cycle. Constructing this observatory required generations of unwavering dedication, a continuous transfer of knowledge that allowed them to encode celestial time into a permanent physical form. Yet this profound understanding of the cosmos was a global phenomenon, emerging independently across the world. Far across the Atlantic, in the lush jungles of Central America, another civilization was building its own stone dialogue with the heavens. 13 stone towers march along a Peruvian desert ridge, a fossilized backbone against the sky. This is Chankillo, the oldest known solar observatory in the Americas, a masterpiece of celestial timekeeping carved into the landscape over 2,300 years ago. Its design is breathtakingly direct. From two carefully positioned viewing platforms on either side of the ridge, a witness could watch the sun rise or set in perfect alignment with the towers. On the December solstice, the sun would rise at the far right of the row. Each day, its position would shift, moving steadily along the spine of towers. Half a year later, on the June solstice, it would crown the final tower on the far left before beginning its slow journey back. This was not a monument for a single dramatic moment, but a complete, publicly visible calendar. For an agricultural society living in a challenging desert environment, this precision was life itself. The entire community could see exactly when the rivers would swell, when to plant their crops, and when to prepare for harvest, all dictated by the sun's reliable passage between these ancient stone sentinels. Chankillo reveals a profound truth that echoes from Stonehenge to these Peruvian hills, a universal human realization that the sun's path is the most dependable clock we will ever know. This principle of solar alignment became a cornerstone of ancient science, yet some cultures sought to measure something even more ambitious than the sun's annual journey. They looked to the stars, aiming to capture the vast, slow turning of the cosmos itself. These four celestial moments, the solstices and equinoxes, formed the unshakable foundation of the ancient world. They were more than just dates, they were the pillars of time itself. The summer solstice, with the sun at its highest and the day at its longest, was a celebration of life at its peak, a time of warmth and plenty. In stark contrast, the winter solstice held a quieter, more powerful magic. It was the shortest day, the deepest point of the cold, and yet it carried the profound promise of the sun's return, a symbol of rebirth that gave people hope through the hardest season. Then came the equinoxes, those two perfect days of balance each year when light and dark stood in equal measure. They represented a universal harmony, a fleeting moment of cosmic equilibrium. For the first astronomers, identifying these days with absolute precision was not an academic exercise, it was a direct line to survival. Their entire agricultural cycle, from planting to harvest, depended on it. Their religious ceremonies and the very structure of their society were synchronized to this celestial clock. So how did they catch the sun at these precise turning points? They became masters of the shadow. At noon on the summer solstice, a vertical object casts its shortest shadow of the entire year. On the winter solstice, that same object casts its longest, most stretched out shadow. The equinoxes are marked by the sun rising and setting due east and west, creating a perfect line of symmetry. By placing a single stone pillar, a gnomon, and carefully tracking the path of its shadow's tip throughout the year, they could see this beautiful, predictable pattern unfold. They would witness the shadow's path draw a long, sweeping curve day by day, and they learned to identify the exact day it stopped and turned back, the solstice. Marking that spot with another stone created a permanent, physical record of that celestial event. This simple act of observation and marking transformed the abstract movement of the heavens into a tangible, community-wide calendar etched into the earth. It ensured that everyone knew when to prepare the fields, when to honor the gods, and when to gather together, keeping the entire society in a sacred rhythm with the world around them. This deep understanding of solar time was a monumental achievement, yet some cultures looked beyond our own star to build a calendar of breathtaking complexity and accuracy. A single, upright stone could reveal the deepest truths of the cosmos. This was the Gnomon, the fundamental instrument of the first astronomers. Placed firmly in the earth, its shadow became a dynamic, ever-changing clock and calendar. At the precise moment of local noon, when the sun reached its highest point in the sky, that shadow pointed unerringly toward true north, giving the ancient world its most reliable compass. But the real magic unfolded over the seasons. If you marked the tip of that noon shadow every single day, you would see it trace a beautiful, predictable pattern over the course of a year. In the height of summer, the shadow would be at its absolute shortest. Day by day, it would grow longer until it reached its maximum stretch on the shortest day of the year, the winter solstice. Then it would pause and begin its slow retreat back. By placing stones at these turning points, the longest and shortest shadows, a community created a permanent public calendar etched directly into the landscape. This simple act transformed an abstract celestial event into a physical reality everyone could see and understand. The Gnomon did more than just mark the solstices, however. By carefully tracking the entire arc of its shadow from sunrise to sunset on a single day, an observer could divide the day into reliable segments, creating the world's first sundial. From this humble stick, they could measure the hour, the season, and even deduce the Earth's tilt on its axis. This universal language of shadow and light was a gateway to understanding our place in a vast, orderly universe. The daily ritual of tracking the sun's shadow was a practice of profound patience. An ancient astronomer would select a level piece of ground and plant a single vertical rod, the Gnomon. At the exact moment each day when the sun reached its highest point, casting the shortest shadow, they would carefully mark the shadow's tip with a small stone. Day after day, season after season, they would watch this point migrate. It would journey steadily southward as the days grew shorter and the sun sank lower in the sky, reaching its farthest southern point on the winter solstice. Then it would pause and begin its slow return journey north, culminating at the summer solstice. The two stones marking these extreme points became the anchors of the year, the undeniable proof of the sun's turning points. But the astronomers did not stop there. They then found the precise midpoint between these two solstice markers. The days when the noon shadow touched this central point were the equinoxes, the moments of perfect balance between light and dark. This simple, repetitive act, requiring years of dedicated observation, yielded one of humanity's first great scientific instruments, a solar calendar etched directly into the Earth. In ancient Egypt, this principle was scaled to a monumental level. Their towering obelisks acted as giant gnomons for the entire community, their immense shadows sweeping across public squares and marking the passage of time for all to see. This daily connection to the cosmic cycle was woven into the very fabric of society. Yet, this method of a single daily measurement, while powerful, only captured one dimension of the sun's journey. To truly map the sky, they needed to follow the shadow from dawn until dusk. This second method required no tools at all, only a keen eye and a deep familiarity with the land. While some cultures were etching calendars into the ground with shadows, others were reading the sky directly, using the horizon itself as their instrument. They learned to watch the precise point where the sun first peaked over the eastern hills at dawn, or where it finally vanished behind a western ridge at dusk. Throughout the year, this rising and setting point does not stay in one place. It migrates along the horizon, traveling northward as the days grow longer in spring and summer, then reversing its journey southward as autumn deepens into winter. The solstices are the boundaries of this journey, the farthest north and south the sun will ever appear. An ancient farmer might notice that every year the sun seemed to pause and rise from the exact same gap between two distant mountain peaks just before the coldest weather arrived. That specific alignment became a reliable signal, a natural announcement that the winter solstice was here. Another observer might see the summer solstice sunset fire the tip of a single prominent rock pillar, a blazing confirmation of the year's peak. This knowledge was not locked away in a temple, it was shared by the entire community. It was portable, adaptable wisdom. A hunter following a migrating herd could use a new landmark to gauge the time of year. A family moving to a new valley would quickly learn the local celestial markers, integrating their calendar into the new geography. This horizon calendar turned the entire world into a vast, open-air observatory, where the simple act of looking at the sunrise could tell you everything you needed to know about the season. It was a living science woven directly into the rhythm of daily life and the very shape of the land they called home. This profound connection between earth and sky would eventually inspire something more permanent, a desire to build markers that would stand for generations, cementing this celestial knowledge in stone. The ultimate expression of this celestial knowledge was to build it into the very bones of the landscape, to engineer monuments that would speak with the sun and stars for generations. This third method moved beyond temporary markers and natural horizons, demanding a staggering long-term vision. It required not just precise observation, but advanced engineering, a society unified enough to dedicate centuries to a single project. The goal was to capture a celestial event in stone, to create a moment of pure magic. Across the world, from the passage tombs of Ireland to the pyramids of Egypt, architects designed structures so that on one specific, critical day of the year, light would perform a miracle. A single beam of sunlight would pierce a long, dark corridor, travel its entire length, and finally illuminate a sacred chamber deep within the earth. This was not a vague alignment, it was a precise, repeatable, and deeply symbolic performance of cosmic order. In Ireland, the massive mound of Newgrange stands as a perfect example. Above its main entrance, a special opening known as a roof box was constructed with incredible care. For the entire year, the inner chamber remains in deep shadow. But for a brief period around the winter solstice, at the very moment of sunrise, something extraordinary happens. A narrow beam of sunlight enters through the roof box, penetrates the long passageway, and for just 17 minutes, it floods the central chamber with a golden light, illuminating ancient spiral carvings. This dramatic event was a powerful confirmation of the sun's return, a blend of science, religion, and art that must have inspired awe in all who witnessed it. These monuments were more than temples, they were eternal calendars, designed to outlast empires and keep humanity's sacred appointment with the cosmos. They prove that our ancestors were not just watching the sky, they were building a permanent dialogue with it. Yet the sun was not the only timekeeper in the ancient sky. The moon presented a far more complex puzzle, a celestial companion with its own mysterious rhythm. Its silver light governed the night, its phases marking a shorter, more intimate cycle of weeks rather than seasons. But the moon's full dance was far more elaborate. While the sun faithfully traces the same horizon path year after year, the moon embarks on a much longer journey. Ancient astronomers discovered that the points on the horizon where the moon rises and sets slowly shift over a cycle of 18.6 years. This long rhythm culminates in a lunar standstill, a period where the moon reaches its most extreme northerly and southerly positions, far beyond where the sun ever travels. Evidence carved in stone suggests they not only observed this, but mastered its prediction. At Stonehenge, the arrangement of the iconic sarsen stones and the smaller blue stones appears to create precise sightlines toward these extreme moonrise and moonset points. To encode this 18-year cycle into a permanent monument meant generations of people meticulously passing down this precise knowledge, a testament to their dedication to understanding the cosmos. This lunar knowledge was not merely theoretical, it was absolutely essential for creating a practical calendar that worked in the real world. The solar year is about 365 days long, but 12 cycles of the moon's phases only add up to 354 days. This 11-day discrepancy would quickly throw any calendar into chaos, causing the seasons to drift through the months. The solution was the lunisolar calendar, a brilliant innovation that reconciled the lunar month with the solar year by periodically adding an extra month. This complex interlocking of two celestial clocks was vital for scheduling everything from sacred rituals and public festivals to the timing of trade and taxes. The moon's ever-changing face added a deep, resonant layer to their model of the universe, a rhythmic pulse of silver against the steady, golden march of the sun. How did this profound understanding of celestial mechanics influence the very structure of their society and their most sacred beliefs? Buried in a German forest for 3,600 years, a small bronze disc held a secret that rewrites our understanding of the Bronze Age mind. Known as the Nebra sky disk, it is the oldest known concrete map of the cosmos ever discovered. This was not a monument of stone, but a portable masterpiece of metal, a physical summary of the heavens that one person could hold in their hands. Inlaid with gold against a blue-green patina, the symbols are unmistakable: a sun, a crescent moon, and a cluster of stars believed to be the Pleiades. This was far more than a simple decoration. It was a sophisticated instrument designed to solve the very calendar problem that challenged early astronomers. The disk's true genius lies in the two golden arcs added to its sides later in its history. Researchers believe these arcs represent the precise angle on the horizon between the sunset points at the summer and winter solstices. Imagine a community elder holding the disk aloft, aligning it with the actual horizon. By matching the arc to the sun's seasonal path, they could determine exactly where they were in the yearly cycle, using this handheld device to synchronize the lunar months, marked by the symbol on the disk with the solar year. It was a compact, brilliant calculator, a bridge between the immense cycles of the sky and the practical needs of a society that depended on accurate timekeeping for planting, harvest, and ceremony. The Nebra sky disk reveals that this celestial knowledge was not locked away in massive, immovable temples. It was a living science condensed into a valuable, mobile object. It proves that the principles of horizon calendars and lunisolar synchronization were understood widely enough to be encoded in metal, a testament to a shared and profoundly advanced vision of the cosmos. This shared celestial curiosity sparked a global conversation, a silent dialogue etched into stone across every continent. High on a sun-baked butte in Choco Canyon 1,000 years ago, a community engineered a moment of pure theater. They carefully placed 3 large stone slabs so that, as the sun climbed on the summer solstice, a dagger of light would pierce the shadow and plunge directly into the heart of a spiral petroglyph carved on the cliff face. This sun dagger transformed a rock art panel into a dynamic solar calendar, a precise and public announcement of the year's turning point. Far to the north, on the windswept plains of Wyoming, the Big Horn Medicine Wheel spreads its stone spokes across a high mountain meadow. Its cairns and alignments do not point to a single event, but to a symphony of celestial movements, marking the summer solstice sunrise and the rising of key stars like Sirius and Aldebaran. This was not an isolated temple, but an open-air observatory that wove the sun and stars into a single, unified map of the heavens. The ambition for precision knew no bounds. In ancient Egypt, the builders of the Great Pyramid achieved a feat of alignment that still baffles engineers today. Its massive base is oriented to the 4 cardinal directions with an error of less than 1/15th of a single degree, a level of accuracy that suggests a profound, long-term study of the stars, likely using the circumpolar stars to find true north. Meanwhile, on the other side of the world, Chinese astronomers refined the humble Gnomon into a powerful scientific instrument. They used these towering shadow casters not just to tell time, but to perform a calculation of breathtaking scale, measuring the size of the Earth itself by comparing shadow lengths at different latitudes. From the deserts of Peru to the plains of North America, from the Nile Valley to the Yellow River, humanity was engaged in the same great project. We were all asking the same fundamental questions about time, order, and our place in the universe. And everywhere we found answers using the most universal tools imaginable: stone to mark the earth and shadow to measure the sky. This was not a secret knowledge passed between cultures, but a parallel awakening, a shared heritage written in the silent language of astronomy. It reveals a deep, innate human drive to find pattern and meaning in the cosmos, a drive that would eventually lead to an even more profound realization, one that connected the rhythm of the heavens directly to the cycle of human life. The geometry these astronomers mastered was not confined to parchment, but was etched into the landscape itself. They wielded a form of mathematics that was both elegant and profoundly practical, built upon principles we still use today. The concept of similar triangles was their silent partner in discovery. Imagine 2 Gnomons, identical in height, planted in the earth hundreds of miles apart. If at the exact same moment on the same day, one casts a long shadow while the other casts almost none, what does that tell you? It reveals the curvature of the earth itself. The Greek philosopher Eratosthenes performed this very experiment in the 3rd century before the Common Era. By comparing the shadow length at Alexandria with reports of no shadow at Scene, he calculated our planet's circumference. His result was accurate to within a few percent of the modern value, a staggering feat achieved with little more than a stick, a shadow, and a brilliant geometric insight. This was not abstract number crunching, it was applied mathematics born from an intimate dialogue with the natural world. The same principles allowed them to measure what seemed unreachable, using the length of a shadow to calculate the height of a tree, a pyramid, or a mountain. Their tools were simple ratios and proportions, a language of relationship and scale that turned the world into a solvable puzzle. But their mathematical genius extended far beyond geometry. The most fundamental act of all was counting. They kept meticulous records, carving tally marks on bone or stone to track the days between lunar phases, the years between eclipses, the slow procession of the seasons. These marks were more than just numbers, they were the first datasets, revealing the ratios that govern the cosmos. They learned that 19 solar years almost exactly equals 235 lunar months, a cycle that allowed them to synchronize the sun and moon in their lunisolar calendars. Every mark was a step toward predicting the future, a way to impose a beautiful, reliable order upon the seeming chaos of the world. Their calculations, though built from simple steps, were profoundly effective because they were rooted in observation and necessity. This mathematical foundation, written in shadow and stone, would become the bedrock for all the science that followed. The cosmos was their sacred text, its cycles a divine language spoken by the gods themselves. For the first astronomers, a solar eclipse was not merely a celestial event, It was a moment of profound spiritual crisis, a temporary victory of darkness over light. The ability to predict such an event, to stand before a terrified community and announce the sun's return, granted the priest astronomer a power that felt almost supernatural. This was knowledge that could calm a panicking population, that could reinforce the social order, and that proved a direct line to the divine will. The great monuments they built were never just observatories, they were the very intersection of earth and heaven. A tomb like Newgrange was designed so that on the winter solstice, the sun's light would pierce the darkness of the burial chamber. This was a powerful, tangible symbol of rebirth, directly linking the sun's promised return to the human hope for life beyond death. The pyramid, pointing to the circumpolar stars that never set, was a stairway to an eternal afterlife. The entire cosmic order, from the reliable sunrise to the slow precession of the stars, provided a grand, comforting narrative. It explained chaos as part of a larger pattern, and it gave humanity a role and a purpose within that pattern. By building Stonehenge or Chankillo, they were not simply tracking time, they were actively participating in a sacred dialogue, helping to ensure the sun would turn back, the seasons would cycle, and the world would remain in balance. This deep, spiritual conviction was the true engine behind these colossal projects. It was the force that motivated generations to haul stones across impossible distances, to carve precise alignments with rudimentary tools, and to meticulously pass down knowledge for centuries. They were not just studying the universe, they were fulfilling a cosmic duty, cementing their place within a living, breathing, and orderly whole. This long-term project demanded more than individual genius. It required a society capable of thinking in centuries. The most profound challenge these first astronomers faced was not mathematical, but human: how to preserve a complex science across hundreds of years without a single written word. Their solution was a masterpiece of cultural engineering, weaving knowledge into the very fabric of their community. The elders did not lecture from scrolls, they sang the stories of the stars. They composed epic poems that encoded the 18.6-year lunar cycle in their verses, and they choreographed dances that physically mapped the sun's journey along the horizon. Every ritual, from a solstice celebration to a coming-of-age ceremony, was a living lesson, a performative act that tied human life directly to the cosmic clock. The true classroom, however, was the sky itself. An apprentice would spend decades at the side of a master, not just listening but watching. They learned to recognize the subtle shift in a star's position, to feel the changing angle of the wind as a season turned, and to interpret the specific quality of light at a solstice sunrise. This was knowledge earned through patient, sensory immersion, a deep literacy of the natural world that could never be captured fully on a page. Yet they also built a permanent, fail-safe backup for this living tradition. The great stone circles and corridor tombs were not just for ceremony, they were eternal textbooks carved from rock. A society could suffer turmoil, its songs and stories could fade, but if even a single generation remembered to watch the horizon on the morning of the winter solstice, the monument would speak. The sun would rise in perfect alignment, the light would pierce the inner chamber, and the knowledge would be reborn. This intergenerational handshake, this sacred trust between ancestors and their descendants, is one of humanity's most stunning achievements. It reveals a culture with a deep, abiding reverence for the future, a people who built clocks not for themselves but for grandchildren they would never meet. Even the most brilliant minds are bound by their tools and their time. For all their ingenuity, the first astronomers worked within a cage of constraints we can scarcely appreciate today. A single overcast week could be a catastrophic data loss, completely obscuring the critical sunrise of a solstice or the delicate crescent of a new moon. Their entire calendar depended on a clear line of sight to the horizon, a view that could be blocked by a rogue weather pattern for the precise days needed to mark a turning point of the year. Their finest instrument was the human eye, remarkable in its sensitivity but limited in its resolution. They could not see the moon's craters as anything more than faint shadows, nor could they resolve the distant planets as disks. Their entire cosmos was framed by the local topography, the hills and valleys that defined their personal horizon. This meant the exact timing of a solstice sunrise could vary from one valley to the next, a local truth rather than an absolute one. A deeper, more insidious challenge was at work, one that moved slower than a human lifetime. The Earth's axis slowly wobbles like a spinning top over a vast cycle of 26,000 years, a phenomenon known as precession. This gradual shift means that the pole star changes over millennia, and the rising position of every star imperceptibly drifts. A temple perfectly aligned with a bright star's rise would, over centuries, find that star had drifted away from its sacred sightline. The very fabric of their celestial map was in constant, if glacial, motion. Furthermore, they interpreted everything they saw from an Earth-centered perspective. The sun, moon, and stars quite literally appeared to revolve around a stationary world. They had no reason to believe otherwise, and their geocentric model was a perfectly logical conclusion drawn from direct, daily evidence. Yet within this bounded reality, their achievements are what truly stun us. They took these limitations not as barriers, but as the defined rules of a grand puzzle. They compensated for weather with patience, repeating observations year after year to confirm their findings. They overcame the limits of the eye with communal knowledge, sharing and comparing sightings across generations. They built monuments not just for their own time, but with the foresight that their descendants would need to recalibrate the slow dance of the stars. Their success is a powerful testament to the human spirit, proving that profound truth can be uncovered not with perfect tools, but with relentless curiosity and impeccable logic. The echoes of their work are written into the very structure of our modern world. Look at the calendar on your wall. Its 365 days, a direct inheritance from their relentless solar counts. Even the way we measure angles, dividing a circle into 360 degrees, is thought to be a beautiful geometric fossil from their early estimate of the days in a year. This was more than just timekeeping, it was the birth of a mindset. Their patient, repeated watching of the sky established the most fundamental principle of all science, the power of careful observation to reveal a predictable pattern in nature. This legacy is not locked in the past. Today, the field of archaeoastronomy is experiencing a renaissance, armed with tools those first astronomers could never have dreamed of. Laser scanning from aircraft, known as LiDAR, can strip away dense forest canopies to reveal vast, hidden ceremonial landscapes. Sophisticated 3D modeling software allows researchers to test alignments with incredible precision, simulating the sky as it appeared thousands of years ago to confirm an ancient sightline. Each new discovery reinforces a profound and humbling truth. The journey that culminated in the Hubble telescope gazing at the edge of the universe did not begin in a modern laboratory. It began with a single person on a clear morning long ago, patiently marking the tip of a shadow and wondering about its meaning. The most persistent myth about these ancient wonders is also the most dismissive of human genius. A popular story suggests that only visitors from another world could have aligned these stones with such precision. This idea does more than spark imagination. It fundamentally robs our ancestors of their greatest achievement. We have overwhelming evidence that these were profoundly human endeavors. Archaeologists have uncovered the quarries where the stones were cut, the stone and copper tools used to shape them, and the remains of worker settlements complete with bakeries and medical facilities. We have even found the engineering mistakes, the cracked lintels at Stonehenge and the abandoned pyramid at Medum, which testify to a long process of trial and error. These were not projects completed overnight by advanced technology. They were the work of generations, a continuous transfer of skill and celestial knowledge from parent to child, from master to apprentice. The true marvel is not a fictional spaceship, but the sheer force of human patience and collective effort. It is the story of a culture that could look at the wandering sun and dream of capturing its path in a circle of stone that would stand for millennia. That reality, the fact that people just like us achieved this with their minds and their hands, is a legacy far more inspiring and wondrous than any alien intervention. But the ancient astronomers' toolkit was not limited to stone and shadow alone. When the sun vanished behind clouds or set for the night, their work continued with a suite of ingenious auxiliary instruments. In ancient Egypt, a device called the merkit transformed stargazing into a precise science. It was a simple yet brilliant tool, just a palm rib with a vertical slit, used in a pair with a plumb bob. An observer would hold one merkit to sight a specific star through its slit, while an assistant, standing a known distance away with a second merkit, would ensure both were perfectly aligned. By tracking a star's path across the sky this way, they could determine the time of night and establish true north with astonishing accuracy, laying out the foundations for their temples and pyramids. For measuring the passage of hours independent of the sun, they relied on the clepsydra or water clock. This was a simple vessel filled with water that dripped out at a steady rate. Marks on the inside of the pot indicated the hours as the water level fell, providing a reliable measure of time through the long, star-filled nights or during overcast days. They even turned to the element of water for celestial observation itself. A still, reflective pool could act as a perfect artificial horizon, allowing an observer to watch the reflection of a star or planet without straining their neck, creating a stable, calm platform for measurement. Later, these principles of mapping the sky would culminate in the astrolabe, a complex portable computer made of metal discs that could solve problems of time and the position of celestial bodies. This constant refinement of tools, from the humble water clock to the sophisticated merkit, reveals a culture in a state of perpetual innovation. They were not content to simply watch the sky. They were driven to measure it with ever greater precision, extending their reach beyond the limitations of daylight and weather, pushing the boundaries of what was possible with the materials they had at hand. This celestial map was not confined to the land. The very same skills that measured the seasons became the foundation for the greatest journeys in human history, guiding explorers across trackless oceans. Once you understood that the heavens were a predictable, rotating sphere, you could use them as a universal guide. In the northern hemisphere, the North Star, Polaris, held a special secret. While all other stars appeared to wheel through the night, Polaris remained almost perfectly fixed, a luminous pivot point in the sky. By measuring its angle above the horizon with a simple cross staff or even a fist held at arm's length, a sailor could determine their latitude, their north-south position on the globe. The sun, too, became a daytime compass, reaching its highest point at local noon and casting a shadow that pointed unearly toward true north. But the ultimate masters of this celestial art were the Polynesian navigators. Venturing into the vast Pacific in double-hulled canoes, they possessed no magnetic compasses or charts. Instead, they carried a mental map of the entire ocean, built on a lifetime of observation. They memorized star paths, knowing which specific stars rose and set over each of their destination islands. They learned to read the subtle patterns of ocean swells, feeling how they refracted around unseen islands hundreds of miles away. They watched the flight patterns of seabirds, knowing which species would fly out to sea to fish and return to land at dusk. This was not guesswork. It was a sophisticated, living science passed down through generations of master navigators. Their canoe was a moving observatory, and the sky was their unchanging chart. This ability to navigate by the stars transformed the world, enabling the exchange of goods, ideas, and traditions across impossible distances. The same cosmic clock that told a farmer when to plant his seeds now guided a ship toward a new horizon, weaving the destiny of continents together with threads of starlight. This celestial calendar was the bedrock of civilization itself. The most urgent life-or-death application of this knowledge was agriculture. Knowing the precise date of the winter solstice told a community that the coldest days were ahead, a time to ration stored grain and protect livestock. The spring equinox, with its perfect balance of light and dark, was the universal signal to prepare the fields and sow seeds, ensuring crops would have the full warmth of the sun to grow. The summer solstice marked a period of growth and vigilance, while the autumnal equinox was the undeniable call to harvest, to gather the bounty before the weather turned. This was not a matter of guesswork or tradition alone. It was a schedule dictated by the cosmos, and its reliability transformed human society. For the first time, farmers could plan with confidence. This precision led to surplus, to grain stores that could feed a population through a lean year. That surplus was the catalyst for everything that followed. It meant that not every person had to spend their days in the fields. Some could become artisans, crafting tools and pottery. Others could become soldiers, administrators, or builders. This specialization of labor is the very definition of a complex society, and it was all built on the foundation of an accurate calendar. The individuals who held the knowledge of the skies, the astronomer priests, became the most vital figures in the community. Their ability to read the heavens and announce the turning points of the year directly ensured the people's survival and prosperity. Their predictions governed the rhythm of life, from the largest harvest festival to the most personal act of planting a seed. This created a powerful, self-reinforcing cycle. Successful agriculture produced the food surplus that supported a large, non-farming workforce. That workforce could then be mobilized to construct the massive stone observatories, the very temples that allowed for even more precise celestial measurements. Those improved measurements, in turn, led to better crop yields and greater surplus. Astronomy was not a passive observation. It was the active engine that drove the growth of cities, trade, and culture. The great monuments we marvel at today were not just symbols of power. They were the indispensable infrastructure that made that power possible. This pursuit of cosmic order was expressed through a profound architectural beauty. The stones they raised were not placed at random. Their geometry was a deliberate echo of the heavens. The stark symmetry of a pyramid pointing to the eternal stars, the perfect circle of a henge mirroring the cyclical path of the sun, the long processional avenue of a city aligned to the solstice dawn. These were not just engineering feats. They were a physical language, a way of speaking about balance, harmony, and humanity's place within a vast divine system. To walk through such a space was to experience a powerful feeling of connection, a sense that the human world and the cosmic world were one and the same. The very stones underfoot were in conversation with the stars overhead, creating an environment where one could not help but feel part of a grand, intelligent design. This foundational idea that true beauty is found in alignment with the fundamental laws of nature has never truly left us. It resonates in the serene proportions of a classical temple, in the soaring verticality of a cathedral reaching toward the heavens, and even in the clean lines of modern architecture that seeks to bring the orderly patterns of nature indoors. Their legacy is the understanding that our most inspiring spaces are those that make us feel connected to something greater than ourselves. They built these monuments not merely for the utility of marking time, but to inspire a lasting state of wonder, a feeling that the entire universe is, at its heart, beautifully and intelligently arranged. For centuries, the profound astronomical alignments of ancient sites were dismissed as random chance or the work of later civilizations. The sheer intellectual leap required to see a stone circle as a computer was simply too great for the academic world to make. Then, in the 20th century, a quiet revolution began. A Scottish engineer named Alexander Thom brought a new kind of precision to the old stones. He spent decades meticulously surveying hundreds of stone circles across Britain, measuring their layouts with the exacting eye of a man who understood geometry and engineering. His data revealed something startling. The stones were not placed haphazardly. They formed perfect circles, ellipses, and egg-shaped rings built with a standardized unit of measurement he called the megalithic yard. More importantly, he identified lines of sight that pointed to the extreme rising and setting positions of the sun and moon. His work suggested a pan-European tradition of advanced astronomy. Soon after, an American astronomer named Gerald Hawkins turned his attention to the most famous monument of all, Stonehenge. Using an early computer, he fed in the positions of the stones and ran simulations of the sky from thousands of years in the past. His results, published in the 1960s, sent shockwaves through the archaeological community. He demonstrated that the many alignments at Stonehenge were far too numerous and precise to be accidental. The monument, he argued, was an ancient observatory designed to predict solstices, equinoxes, and even eclipses. This was the true birth of modern archaeoastronomy. It forced a complete re-evaluation of our prehistoric past, proving that deep scientific thought existed long before the written word. We had to learn to see these places not as temples of superstition, but as laboratories of cosmic order. Today, this field continues to uncover breathtaking secrets, reminding us that the quest to understand the universe is humanity's oldest and most enduring story. From a single stone catching a shadow to the grand celestial computers of Stonehenge and Chankillo, this journey reveals a profound truth about human potential. Our ancestors, armed with nothing but patience and relentless observation, achieved a scientific precision that still commands our respect. They proved that the tools for measuring the universe are not found in complex machinery, but in the disciplined human mind and its capacity to see patterns in the world. Their legacy is woven into the fabric of our daily lives, present in the 365 days of our calendar, the directional certainty of our compass, and the very foundation of the scientific spirit that seeks to understand the natural world. The next time you notice the long shadow of a tree stretching across the ground at sunset, or trace the time on a simple sundial, you are witnessing the very same principle that once guided entire civilizations through the turning of the seasons. Let this journey inspire you to look up at the night sky with fresh eyes, to see it not as an impenetrable mystery, but as the first great map, one that our ancestors began charting for us in stone and shadow long ago. If you found this exploration of our shared cosmic heritage fascinating, we invite you to subscribe for more journeys into the wonders of the past.